Welcome to today's explainer. Think about the device you're using right this very second. It honestly feels a bit like magic, doesn't it? You tap a smooth piece of glass, type on a keyboard, and boom, complex applications just spring to life. But as we all know, it isn't magic at all. There's an entire microscopic engine humming away right beneath your screen. So today, we're going to strip away those sleek user interfaces and reveal the completely fascinating hardware secrets that actually power our modern world. Especially for those of you studying computer science or IT, I really want you to look past your high-level code for a moment. You're out there writing scripts in Python, Java, or C++, and your programs run flawlessly. But what is physically executing those commands? How does a typed command actually turn into a physical action inside a machine? Well, that is the exact mystery we're going to unravel today. Okay, let's dive into this. Here's our roadmap for today. We'll start with the digital world, move to analog versus digital, learn the binary language, see how digital systems work, and finally, bridging hardware and software. All right, Section 1, the digital world. Before we zoom in on the microscopic details, we really need to take a second and appreciate the sheer ubiquity of the technology we interact with every single day. Whether you're firing off a text, grabbing cash from an ATM, or sitting in a smart vehicle, it is digital electronics silently running the whole show. It's literally the absolute foundation for everything from the Internet of Things and massive communication networks to cutting-edge AI hardware and life-saving medical equipment. It's everywhere. Moving on to Section 2. Analog versus digital. So we know this tech is everywhere, but to really wrap our heads around how it works, we have to explore this fundamental divide between the physical world we actually live in and the computing world we've built. See, our real physical world is analog. Analog signals are continuous. They represent an infinite range of values. Think of a radio signal or the output from a microphone capturing my voice right now. But that messy, continuous nature makes analog highly susceptible to electrical noise and, honestly, very difficult to store accurately over time. Digital electronics, on the flip side, operates on discrete binary signals. It completely strips away those infinite possibilities and uses just two distinct clean states, 0 and 1. This brilliant simplification makes digital systems highly resistant to noise and incredibly easy to store, copy, and process. But wait, here's the challenge, right? Since our physical world is super messy and analog and our computers absolutely require clean, discrete, digital data, how do they even talk to each other? Well, we use this brilliant little device called an analog-to-digital converter, or ADC. This thing acts as the ultimate translator. It takes that continuous real-world information and slices it up into discrete digital data, all so embedded systems and computers can actually understand and interpret it. Which brings us to Section 3, the binary language. Once that analog translation actually happens, we officially enter the realm of the only language our hardware truly understands. So the crucial point is this. The foundation of absolutely all digital systems comes down to just two tiny numbers, 0 and 1. But here's the kicker. They aren't just abstract math. In digital electronics, these numbers represent physical discrete voltage levels. A 0 represents a low state, which basically means the absence of voltage. And a 1 represents a high state, the presence of voltage. By relying on just these two incredibly stable physical states, digital systems can achieve mind-blowing accuracy and reliability. Now, what's really interesting here is how this abstract math becomes super concrete. Everyday decimal numbers translate purely into combinations of these high and low voltage states, which we call bits. Take the number 5, for instance. In the digital world, that translates to the binary sequence 0101. Every single piece of information, whether it's a number, a letter of the alphabet, a super high-resolution image, or a 4K video, is completely broken down into these specific combinations of zeros and ones. And the coolest part? They scale up beautifully. One individual 0 or 1 is a single bit, just one binary digit. But group 4 of them together and you've got yourself a nibble. Group 8 bits and you have a byte. Scale that up to 1,024 bytes and you're looking at a kilobyte. Every digital device on the planet stores and processes data just by stacking these simple binary representations on top of each other. To put that into perspective, a single gigabyte on your smartphone, that's over 8 billion of these individual ones and zeros, all perfectly organized. It's honestly mind-boggling. All right, on to Section 4, how digital systems work. Okay, so we have the language down, but how on earth do these zeros and ones actually accomplish tasks? Well, the true hero of the story is the transistor. You can basically think of a transistor as a microscopic electronic switch. It functions purely as a digital switch, operating in either an on or an off state, which perfectly mirrors our high and low voltages, our ones and zeros. When a modern computer does, well, anything at all, it is relying on millions or honestly even billions of these tiny physical switches rapidly opening and closing to process information. Working together, these switches follow a really simple but incredibly powerful four-step process. First step, input. That's when data is received from a user or sensor. Second is processing, where logic circuits analyze and manipulate that data. Third is storage, meaning memory devices retain the info. And finally, output, where the processed information is actually displayed or put to use. Just think about pressing the number 5 key on a basic digital calculator. The keypad sends a physical binary signal, the processor interprets it, the arithmetic circuit calculates what to do, and the final result gets pushed right to your display screen. Now, diving a bit deeper into that processing step, it relies heavily on what we call logic gates. These are the fundamental building blocks that actually perform logical operations on our binary data. You have gates with names like AND, OR, NOT, NAND, and NOR. By intricately wiring these gates together, the hardware can evaluate multiple different inputs and make very strict logical decisions. That's how we manipulate the binary data to do exactly what we want it to do. And when you start combining these gates, that's when you unlock modern computer architecture. You can build combinational circuits that actively add numbers together and make decisions, and sequential circuits that can actually remember previous actions. Combine those components with memory devices and programmable hardware like microcontrollers or FPGAs, and boom, you've just built a complete, fully functional computer that can be updated entirely through software. And this brilliantly illustrates the real-world trade-offs in digital electronics. The advantages are absolutely massive, right? You get incredibly high processing speeds, total immunity to analog noise, super easy data storage, and amazing scalability that literally lets us pack billions of transistors onto a single silicon chip. But of course, there are limitations. We still need those ADCs we talked about to interact with the real world. High-performance systems chew through a lot of power, and designing these incredibly complex microscopic circuits requires some serious engineering sophistication and intense testing. Finally, let's wrap up with Section 5, bridging hardware and software. So how does all this microscopic machinery actually apply to the code you're writing every day? Well, as the source material states so perfectly, digital electronics provides the hardware foundation upon which software operates. Really, mastering these hardware concepts is what bridges that critical gap between just typing out software syntax and truly understanding computer architecture. Concepts like memory organization, processor design, and logic gates, those are the very reasons your programs are able to execute in the first place. This is exactly where it all comes together. You see, every single line of code you write in a high-level programming language is eventually compiled and translated all the way down into these exact binary instructions. Your if-else statements, your loops, your variables, they all literally become physical sequences of high and low voltages. They are physically executed by the digital circuits, the logic gates, and the billions of tiny transistor switches we've just been exploring. It's all connected. It really shifts your perspective, doesn't it? The code you're writing isn't just text sitting on a screen. It's a set of precise instructions manipulating physical electrical voltage across microscopic switches in real time. Knowing that your software relies entirely on this vast, complex digital architecture, I want to leave you with a quick question to think about. Knowing all this, how will you architect your next digital creation? Because when you finally understand the engine beneath the code, you stop being just a programmer, and you truly start becoming an architect of technology. Thanks so much for joining me on this explainer, and definitely keep exploring the incredible world of digital electronics.